My last talk is about the reduction map of p-adic representations and reduction map. Before explaining what is a reduction map, I planned until yesterday that I'm going to explain what is the motivation of the computation of reduction map. But now I know that some of the participants have to go to the airport as soon as my talk is ended or during my talk. So I think it's better to skip the motivation and explain the definition of reduction map directly. The reduction map is easy. The map is just taking reduction modular P of the representation of the K is a local field, a p-adic field, to the target is a representation over a residue field of the same group. But we taken some semi-simplification, and which is defined for each V in here, taken OE lattice, stable and the GK, taking this reduction modular P. Yeah, this is definition. And take then take semi-simplification, then it is independent of the choice of the lattice. And we would consider only the case where the representation is crystalline. Then in my first talk, I explained this is there is a equivalence of categories between the crystalline representation and then filled out phi merges over E tensor with K0. K0 is the maximum ramified extension of Kp over K over Qp and satisfying some condition named weakly admissible. And this category is equivalent because it is semi-simple, so it factors through the quotient GKTM, which means tamely ramified, maximal tamely ramified quotient of GK. And this group is a very have a very simple description. So this is a semi-direct product, isomorphic to a semi-direct product of Z hat and Z hat prime 1. Prime means that no prime to P part, and 1 is a Tate twist, which describes the action of Z hat and Z hat prime 1. So that source, both in source and target, and in some part very easy to describe. And we have a canonical map from such easy to describe. This is not a functor, this is some object. Isomorphism class is the object. And the problem to describe this map, which shows both of source and target, and easy to describe. And yes, but this problem is rather very difficult to describe in general case, and in today's talk we restrict ourselves to the case of two-dimensional case. When as V is two-dimensional, and also the base field is equal to Qp in the simplest case. So, yeah. And also years. And recall that the corresponding representation is associated to some weak filtered mergers, and the filtered merger has a filtration, then we can have a notion of some Hodge Tate weight, which is a pair of two integers. But without losing any much generality, we can assume that one of the Hodge Tate weights is equal to 0, and can where k is at most 1 by tracing a power of cyclotomic calyx if necessary. Then here. But if k is equal to 1, that problem is not so difficult, and it is rather easy. So we from now on we assume to k strictly larger than 1. In this case, it is of particular importance because the restriction to the decomposition group at P of a Galois representation associated to a p-adic representation associated to a modular form of weight k. In this case, so k is an integer which is at least 2, and in this case for any AP which is a ring, which is an element of ring of integer in OE, and for any unit in OE, there exists D, which is a frequently admissible filtered k module depending on the three plus k, AP, and U, weakly admissible phi module over OE, such that the characteristic polynomial of the operator phi on this D is equal to the 1 minus AP T plus U times P to the k minus 1 times T squared. This is it is not difficult to show by using the condition on weak admissibility, and also we note that D is unique up to isomorphism, if VP is not a unit. If VP is a unit, then the corresponding representation is ordinary, so this filtered phi module is not irreducible, and its semi-simplification is unique, is determined by the K, AP, and U. So the problem is to want to compute
the result when AP is a unit, then you have sort of an extension class that determines, right?
Yes, we can determine we can determine, but I will not explain today. Yes. Also, in such case, the extension class can be already known by using some computation of some Galois cohomology. For example, by using some explicit reciprocity domain. I want to compute the reduction of the representation corresponding to D, K, A, P, U, which is an object corresponding to the weakly admissible filtered phi mergers. Here. So and in some cases Yes. And first we'd like to state the conjecture. So we have U denoted by U modular. U work some and we reach an element in the residue fields and let denote V the variation of AP, where VP is a variation of E normalized as VP of P is equal to 1. And we also denote by D the integer part of V, the largest integer not exceeding V. And we need some extra notation. Let A, K, D denotes the ratio of binomial coefficient whose denominator is equal to IB and the numerator is equal to L minus DB. In most cases, this is, but yes, this lead is smaller than or equal to I. And the other case we put this is equal to infinity. And this is a rational number. And we also need another rational number or infinity. CKD is, this is the sign minus 1 to the L divided by P, and then take I minus 1 over I, and the I minus 2, D is the binomial coefficient, and the L minus D minus 2, and take star. A star means something like this is equal to this rational number, or 0 or infinity. Yeah. It is determined case by case, but I do not like to explain well. But in this is if the details about and P to the minus half and I minus 2D. This part is not so important if D is equal to L minus 1. And third case is at minus 1 to the D and I minus D, I minus 1. I minus 1 D to the 2 D minus L D inverse. And also here taking star if D is larger than L minus 1. Yeah. Again, this is a rational number or infinity. And we put B is, which actually, it in fact depends on K and P and U. Oh, I'm sorry, I did not explain what is D. I'm sorry, what is I? Yeah. We write K minus 1 as in I times P minus 1 plus L, which is, roughly speaking, this is where L is an integer between 1 and P minus 1. And yes, here we use a notation. And let D is here and I is here. Yeah. We also use L here. And B is we define B to the sum of AKD times AP and P to the L times CKD over AP times U. Here. And here we understand infinity plus infinity is equal to infinity. the most important invariant is this.
So what's the conjecture?
I have not stated yet.
Okay.
A conjecture is as follows. This is a joint work with Yamashita. And the first part is that if b is equal to infinity, then the reduction, we denote the reduction by bar reduction, and taking semi-simplification and semi-simplification. Okay. U is isomorphic to the I, U, ver, L, I. And the right hand side was an, okay, I will explain the right hand side here. I don't remember here. And this is where I, U, L for an integer j is, we define it then mu minus square root of u times omega to the L minus D tensor with the induced representation of E to bar to the j to j minus L, where mu something is a ramified character. Its value is that the arithmetic frobenius is equal to alpha, and omega is a multiple cyclotomic character. And epsilon 2 bar is equal to the reduction mod p of the Rubin-Tate character. Of an ramified quadratic extension of QP associated to the prime element P, which is regarded as a uniformizer is an unramified quadratic extension of QP. And this is the first part of conjecture. And secondly, if V is not infinity, let alpha be a root which is an element in a fixed algebraic closure of QP of the polynomial of degree 2 t squared minus b t plus u, and such that and VP alpha, the variation alpha is the smallest among all the roots of this quadratic polynomial, smallest among all the roots. Then this then we divide the situation into two cases. If the first case is a case where the variation with alpha is not an integer, in this case the reduction is also irreducible. U is isomorphic to I, U over L over this is a variation of alpha and take integer part. Okay. And second case in the case where the evaluation of the alpha is an integer. In this case, let's write alpha as a product open unit and the power of p here. When alpha 0 is a unit, then vk ap, the reduction is reducible, and its semi-simplification have the direct sum of two characters, which we denote by r u over l vp alpha alpha 0. Here this guy is then reducible two-dimensional representation. LUJ and some beta, or we have this beta. Beta is a direct sum of two characters. The first one is the unramified character whose value at frobenius is equal to beta, tensored with cyclotron character 2j, and then the next one can be easily mu beta inverse omega l minus j. Yeah. Here the statement of the conjecture.
So is U is a unit?
Well?
U?
Yeah, U is a unit. Yeah,
so
here.
You're supposed to have a U times P to the power or something?
What?
T squared minus P T plus U, it's just U.
Where?
And then we have polynomial here, T squared minus.
Oh, this one?
Yeah.
This is U. Yeah.
It's unit. U is a unit?
Yes, this U is a. Oh, I'm sorry. Yeah, maybe U P to the L. I'm sorry. Thank you very much. Yeah. Yes, this is the conjecture, and the theorem is that. Oh, I'm sorry. This is the conjecture is under the assumption. Suppose that L plus B is larger than or equal to 2I plus 2. And this condition is satisfied. It satisfies for if I is smaller than or equal to p minus 1 divided by 2. So k is so I don't remember. It's about the half over. It's about half over p square. I don't remember how that. Yeah. Something like a p. Here. And the theorem is for this conjecture is true. Oh, this is also Johannesburg. And with the amphitheater, conjecture is true if, except for the case, the following three conditions is satisfied. L is smaller than I, and VP, AP, the variation of the AP is not an integer, and VP, AP is smaller than or equal to L minus 1 divided by 2. If at least one of these conditions is not satisfied, then we can prove the conjecture. Yes, our method is used. We use the theory of Bach module established by Bach, Koolmeets, and Belgian, which gives some equivalence of category between some lattice of Preslin representations under some category of five modules, which they called VAC modules. And actually, we can construct some family of VAC modules, so we can and also we would like to we have to say that our proof is very ugly. We divide the situation into a lot of cases, about 20 cases, and case by case construction of family of VAC modules. And also we'd like to give a historical remark. Such kind of such type of reduction is computed for some cases, especially for the weight is sufficiently small, well k is sufficiently small for our conjecture is also not covered for all k, but for in a notation for I is equal to 0, it is for VP, variation of AP is equal to 0. In this case, it's the ordinary case. For this, I would like to have it make a table later for this case, and but first by I think by Deline, in the case where the representation comes from the global case, global representation, Deline for global case, and then I think by Fontaine, I do not know Fontaine explicit statement, but it follows from the theory of Fontaine, and using Fontaine is using the fund. In this case, very easy because and the other simplest case is a case where the I is equal to 0. In this case, it can be reduction in computing by using the Fontaine-Laplace theory. And when I is equal to 1, in this case, reduction is computed by combining the work of Berger, Breuil, and the Berger Ritsu. The work of Berger and Breuil covers the case where the variation of AP is sufficiently small, and this is done by using the p-adic local Langevin correspondence. By more precisely, the compatibility between the p-adic and multiple Langevin correspondence. And the other case where the variation of VP is sufficiently large, it is proved by the 3 papers by using theory of VAC modules. And also, there for general K, but the condition of VP AP is small. I think this is smaller than or 1. In this case, this is proved by Berzert and G, also by using p-adic local Langevin. And when the variation by AP is sufficiently large, and this case is covered by the method of Belgian, Lee, and Tzu, or other people by using VAC modules. And this is the history. In the proof of the theory, we use the theory of Bach module here. It already appears here. So, first we'd like to explain what is Bach modules. But we restrict ourselves to the explanation to the case where k is equal to qp. In this case, Bach module is such of with the following object. We denote by gm that gm or e hat denote the formal multiplicative group. Or respect OE, this is a formal group scheme of respect OE. We denote by it by W for simplicity because it is essentially equal to that it is a moduli space of some real characters of ZP, so it is essentially equal to the weight space which already appears in the previous talk. And then the group ZP acts in the space as a multiplicative monoid. W, and in fact, ZP is isomorphic to the endomorphism group, endomorphism monoid of the group of W regarded as the group's formal group scheme. So, and we put M in the ZP, but the zero is improved. Yeah.
So what it says?
Okay. What?
What does it say under ZP?
Yes, ZP. We regard ZP as a multiplicative monoid. Yes, actually it's not the abelian group as an abelian group. Yeah. And we define the following simples and vector wonder on some symbol which denote by the quotient of W by M is a free OW module, which is a formal power series with coefficient in OE of finite rank, and equipped with a semi-linear action of each element M of M. This is M. Well, if module M and satisfying some cocycle conditions and conditions of one is equal to identity. The action of one is identity, and the Bach module is we define the Bach module is a vector bundle in this quotient space, quotient-like space, that such that satisfying the following conditions, such that for any element M in M, And the co-kernel, we can consider the co-kernel of the map from some m, then something like a pullback of m of n to n and induced by m. This is a coherent measures over the W is supported. The closure, this is W, but the closure of the torsion point, M torsion point, and subtract the zero section and take in the closure. This is the closure. This is the definition of Bach modules. So maybe I don't have time, but I would like to remark that the Bach module is something like a very similar object. It is a local object, but the module theory of tau modules appears in the previous talk. The difference is as follows. In this case, some affine curve is fixed over a finite field, and also the point is fixed spec k to u. In this case, the Bach module we consider the vector bundle of W over M. In this case, we consider some vector bundle with spec u times spec k, but over the Frobenius tau, the monoid generated Frobenius. This is local object, but this is a global object, so this is a difference. Now the difference is that we have to consider the action of ZP star. This is just to consider the action of P. Where the action, when M is equal to P, then we denote the action P by phi. And the difference, the second difference, the support condition, this one, support is a non-zero torsion point of the multiplicative group. And the theory of T modules support is some diagonal locus. Diagonal means the graph of this morphism. But anyway, both things have some vector bundle with additional structure on some two-dimensional base space. And this is a picture of W, which is something like two-dimensional. And W has two spatial divisors, and one is a zero section, which does move with the spec of OK, and we denote by e to 0 its generic point, and another divisor is a spatial fiber, so the GM hat over finite field. Yes, we denote eta p by beta p is generic point. So, and there is a theorem by it is proved by Belger, but based on the work of Bach and Koolmees. And there exists an equivalence category between the crystalline OE lattice of a crystalline representation with Hodge state weight is negative, maybe positive, or to the category of Bach modules over OE. And an important point is that for a given back measure W, we can easily compute it. It's associated with phi filtered phi measure, and also it's associated with reduction, mode P reduction. And when N is back measure, so the restriction to the generic point of the zero section, we have not explained the filtration of back measure, but there exists a filtration of back measure by using the action of phi, but I have not explained that. But its relation to the generic point of zero section gives it's associated. It sounds like an associated lattice of a crystalline representation gives an decreased V. And also restriction to is either P gives the reduction, the phi gamma measure associated to the reduction measure P of T. So if we constructed that measure associated to some V, then we can compute by using that measure, its direction measure P. And this is a rough strategy to prove the problem by using that measure, and we would like to explain the case, the proof of the theorem. The first step is easy.
So can you just say again words like A to 0
Mm-hmm.
PR?
Mm-hmm.
Can you just say it again?
Oh yes, E to 0 is a generic point of the zero section. Is E to P the generic point of this device? Right? And the first step is we consider the invertible part. This is a ZP minus 0. This is isomorphic to ZP cross. And also its torsion part. And this is isomorphic to mu P minus 1 of ZP. And we regard W over M as a quotient of W over M cross tos over M over M cross tos. This is also isomorphic. This is a finite group closed on an open unit disk by a finite group, so it is also isomorphic to an open unit disk with some parameter x. And it is isomorphic to the 1 plus BCP. And we can take the parameter x, so that the phi is an action of P as an element of M. Phi x is equal to x times P plus x to the P minus 1. Proof of the theorem. Here, I'll explain about what is new about the proof of the theorem. Then the W, there is this finite flat map, W over M cross tos. There I have no time. And which maps the zero section to the point where x is equal to 0, and p torsion point non-zero p torsion point maps to the part where x is equal to minus p. And secondly, the difficulty is in the computation. The construction of the Bach module is difficult because there is no some canonical choice of basis of the Bach module, so it is not difficult unless we fix some basis to compute the reduction, fix the problem of computation. So, but it seems there was not known the nice basis of such a Bach module, but that is partially because of some DOE. We put a DOE in some restriction to the zero section of the Bach module, which gives an integral function of a filtered decreased P. But it is not a strongly divisible lattice. This is a problem. We cannot detect. There is no general theory which detects the lattice of decreased P, which is coming from the Bach modules, which is not strongly divisible. In fact, there is a filtration on this module induced by the filtration of N, but the difficulty arises because the field I is a sub-OE module, but it is not saturated, so the cocoon is not torsion-free. Have a very large torsion. It's not saturated. Yes, our new point is that we considered instead of field I, but the p to the k minus 1 over p to the k minus 1, or the image of phi of field k is the OE. The image of phi, image under phi of field k is by definition of the filtration. It's always divisible by p to the k minus 1, also p to the k minus 1. But this is a submodule of DOE. But this is also, we found after computation proof of the result, we found that this is almost saturated. The torsion of the cocoon is very small. It is often saturated, and the torsion is always very small. And we use this submodule to fix something like basis. And this is the second step. And the third step is that take a basis which the formal proceedings with variable. This n is a vector bundle of here. This is such that something that q k minus 1 phi to the field L of n contains the vector 0, 1, where q is in the phi x over x, so it is isomorphic, is equal to p plus x to the p minus 1. Yes, it follows from the definition of the filtration that the image under phi of the field k of n is divisible by q to the k minus 1. But we put, so there exists some element delta and z which maps by phi to the element 0 q to the k minus 1. we use this notation and satisfy and then describe the condition where the pair of delta and z can come from a Bach module. The problem to reduce find delta and z and an extra element r, which all belongs to the formal power series, such that the following 5 conditions The first condition is that is as follows: p plus x to the k minus 1 minus r times phi z is divisible by phi or delta. And the second condition is that uz over delta plus r over phi delta is congruent to AP over the constant term of delta times 1 plus x over p to k minus 1 over 1 plus phi times delta divided by this constant term to the minus 2 phi over 1 plus phi modular OEX plus e and x to the I minus 1, I plus 1 to the x. So the first I coefficient of this formal power series then is congruent modular and OE. And 3 other conditions is not so important that we'd like to omit. And also, yes, in some cases, this part is also can be ignored. But not all the case, but can be ignored. Yeah. In such case, the problem is reduced to solve. uz over delta is congruent to some AP of delta 7. And the image of phi is very, something like an image, this can be also simplified, but this is 1 plus x over k to the k minus 1. Oh, I have already deleted here. Oh. Yes, and then we use the theory of p-adic approximation. Which is a theory of approximation, a form of power series by a ratio of polynomials, so rational functions. And in the theory, it is known that 1 minus t to the k minus 1 can be approximated by a ratio of certain hypergeometric polynomial. Yes. For example, this can be found by some paper by Voigters and Tishdeman. And we use this hypergeometric polynomial, and we need to establish some. So the problem to reduce to the establish some p-adic property, of these hypergeometric polynomials. Yeah. this is an outline of proof, and this is the end of my talk. But as a final speakers, we would like to thank my sincere gratitude to the organizer and speakers and participants of the conference, to having, especially for organizers to have arranged such a nice place for the conference and very surprise us at a very, very nice Korean traditional food and something of money and a lot of things that nice hospitality. Thank you very much.